Hello everybody. So I'm going to be talking about geophonomics, which is the term we use to describe linking nutrient uptake and fertiliser uptake in the crop with underlying soil properties, so the physical and chemical properties of the soil. So our aim is to gather a large number of paired soil and crop samples from field sites across Africa, and also use the same soils in glasshouse experiments with fertiliser to look at the interactions between different soil properties, physical and chemical properties, so organic carbon content, pH, soil texture, the sand, silt and clay, and the elemental content, to see how that then interacts together to influence what nutrients are taken up into the crop. And we can then build a model based on these interactions. So dry spectroscopic techniques are ideal for these experiments because you can basically screen a very large number of samples because there's very little sample preparation involved. Also, they give you, they're multispectral, so they give you information about multiple soil properties and plant properties in one scan. And they're also cheap because there's very few consumables involved. And the end goal is that we'll then have this model based on soil properties which could predict nutrient uptake. So then a farmer could submit a soil sample for analysis, and based on the soil properties would know the likely nutrient deficiencies and make fertiliser recommendations based on these likely deficiencies. So this would be particularly valuable to smallholder farmers in developing countries who don't necessarily have good access to soil analysis, particularly wet chemistry analysis, and also who can't necessarily afford to apply blanket rates of fertiliser to a crop. They might just be able to afford the fertiliser specific to the deficiency that they have. And this approach would generally apply to a precision farming approach in anywhere in the developing world, where you could just assess exactly what deficiencies your soil has in a particular part of your field and apply the appropriate fertiliser rather than just blanket rates of NPK. So I'll just describe what our DrySpec Lab at RS consists of. So we have a mid-infrared instrument. So this analyses wavelengths of light that are absorbed in the mid-infrared region. So this gives you information about multiple properties because specific molecules absorb specific wavelengths of light. So you could find out about inorganic properties and organic properties all at the same time. And this particular instrument is very high throughput. As you can see, you just need a tiny amount of sample of anything. In this instance, it's soil and plant. And it just needs to be dried and finely ground. And this is the portable X-ray fluorescence instrument. So this tells you about total elemental content of your sample. So similarly to the mid-infrared instrument, it will tell you about multiple elements at one time, because basically as the X-ray is absorbed by the atoms, electrons shift from an inner shell to an outer shell, and that energy fluoresces, and that's exactly specific to different elements. So it will do light and trace elements from sodium to uranium, but generally can't detect anything below 1 ppm. And finally, we have laser diffraction particle size analysis instrument. So this is for to detect sand, silt and clay once you've interpreted the data. So yeah, this uses light diffraction, so the angle that the light diffracts off the particle gives you an indication of what size particle you've got. And we're still in the process of collecting our African paired soil and crop samples and getting a big enough data set, so we don't actually have any model data yet, but I'm going to describe to you the pilot glass house study which we've run to assess basically what ideal methods will be used with Africa soils. So this study used 6 very variable European soils, so sandy and loamy, and some with high organic carbon, and grew them at with or without fertiliser. We also looked at the effect that pot size would have, because we needed to assess how much plant material we could get for use with the XRF instrument, and pot size has an effect on how big your plants get. We also wanted to see at what growth stage was ideal to sample from the plants to see the nutrient effect. So I'll begin with the soil analyses of these 6 soils. So one of the soils, the yellow soil, Casterly, was very sandy and with very low clay. And Leuven, the green soil, was probably what you call sort of a more average soil. So it had more silt and a little bit of clay and a bit of sand. And the other soils were generally much more high clay soils. And some of them also had high organic carbon. Oh, that's gone a bit squishy out. But it's just to show, so this is a correlation between the laser diffraction analysis of soil particle size, or in this case clay, and the relationship to conventional sieve analysis, and it's a good relationship, 0.95, particularly where the organic matter is first removed from the soil, although it does underestimate clay by about 50%, but it's still a good relationship. So looking at the elemental content of the soils which analysed using the XRF, you can see the legends shift down a little bit. So the yellow soil, the Casterly soil, was particularly high in phosphorus, but very low in potassium, which you'd probably expect because it was the really sandy soil with very low clay. And then the Suli soil, which was the blue soil, had particularly high calcium, and that soil comes from the parent material is calcareous, so that's what you'd expect. So this is just to show the soil analysis with the mid-infrared instrument. So if we could compare it to the wet chemistry data on the left in the table, you can see that the soils there with high clay contents have these peaks towards the sort of 3,000, 4,000 wave number region of different clays, so smectite and kaolinite. And these organic carbon peaks relate to the soils here, Arthur Rickwood and Suli soil, which have high organic carbon, according to the wet chemistry. And then these 2 soils, Breckie and Suli, which have high pH, have these high peaks in the calcite region. And the sandy soil, you can see, has these high peaks in the region of quartz. So this is how much information you can gain from one scan about your soils with mid-infrared. So to look at a PCA using this data, you can, on the left, you can see the soils clearly segregate from one another. And the plant material, to some extent, has also segregated based on soil type. and I can't exactly figure out what that spectral region is relating to yet, but I imagine it's something to do with organic carbon content or greenness, basically. So plant PC1 score relates negatively to soil PC1 score, and the PC1 score to some extent is relating to plant biomass. So this suggests that even with just a mid-infrared spectral scan, you might be able to do some predictive modelling of a biomass or yield. And to move on to the, sorry, my graphs have all gone funny. To move on to the nutrient uptake in the plants grown on these soils, which was analysed using the XRF. So, as I said, half of the plants were grown with fertiliser, so they're the filled black bars, and half of the plants were grown without, and they're the open bars. So generally, obviously, you can see that the plants grown with fertiliser have taken up more of all of the nutrients, particularly in the case of not so much in the case of phosphorus, but particularly with sulphur and potassium. The brown bars are what was originally in the soil, so the elemental content of that nutrient in the soil. And you can see with the first graph, with the phosphorus, what was taken up into the plant very closely corresponded to what was originally in the soil. But apart from that, with all the other nutrients, the brown bars don't correspond to the trend of nutrient uptake. So what was originally in the soil didn't really seem to correspond very closely to what the plant took up. So that suggests that with these other elements, that was probably more to do with soil properties and interactions between the nutrients that were added and the soil properties. So I'll just point out that this soil in particular, the green soil, Leuven soil, which I said was the most sort of average soil, which had a little bit of clay and a little bit of sand, but a lot of silt, in all cases really seemed to take up a lot more of the nutrients than the other soils. So that's quite interesting, but I'm not quite sure why yet, because we haven't done the modelling. So, and also this sandy soil, it took up a lot of potassium and a lot of sulphur, and it actually took up less manganese where fertiliser was added, and I think that's some kind of antagonistic interaction between potassium uptake, because you can see potassium uptake with these plants was really high. So that's what we want to figure out with the models, how all these different soil properties interact. And so just to say, so this, we're also doing the same experiment, but with 30 Kenyan soils with very variable soil properties, and also under different minus treatments to see if some soils respond with less deficiency than others. Just to move on to our organic amendments field trial, where we've also looked at the nutrient uptake in relation to different organic amendments which have been applied. So these were anaerobic digestate, which is basically waste from biogas production, and it's fermented, basically a fermented compost. And then just compost, which is obviously biodegraded material, and farmyard manure, which is less biodegraded. And then you've got straw, which has a high carbon to nitrogen ratio, and that affects N uptake because it becomes immobilized by microorganisms. So you would expect that to have some kind of influence on the nutrient uptake. And then there are also mixtures of the amendments with straw. And 4 different rates of amendments were applied, but they all received the same inorganic fertiliser of nitrogen, potassium, sulphur. So the first graph shows straw yield in 2013, which is the baseline year, and the untreated is the white bar. So you can see there's not really any difference in yield in the baseline year. Whereas by 2017, the amendment-only group, which is the dark green bars, you can see have a significantly higher yield compared to the untreated and compared to the straw only. So the straw only will be related to the high C to N ratio that I mentioned, so it doesn't provide as much nitrogen to the crop. So to look at this in relation also to the nutrient content of the crop, which was analysed using the XRF. Again, in 2013, you can see there's no differences between the amended and the untreated. And just to emphasise, actually, this is concentration, not uptake. So you might expect that concentration would be lower in the higher yielding biomass. It's what you call a biomass dilution effect. So because the biomass has got bigger, but the amount of nutrients taken up are roughly equivalent, the concentration of the nutrients might be lower in the higher yielding crop. But actually, by 2017, you can see with all of the nutrients, particularly phosphorus and calcium and sulfur, all of them, that there's higher nutrient concentration in the amended plots, even though they've got a greater biomass. And straw has quite sometimes a slightly higher concentration than the non-straw amended plots, but that's because it had a lower yield, so there is a little bit of biomass dilution going on. And that's it. Thank you to our collaborators at ICRAF in Kenya who are involved in the AFSIS project with us, and my lab group.
Okay, thank you very much, Cathy. Thank you. Time for one quick question for Cathy.
Just was wondering, how do the chemical analysis of some of these soils correspond to some of your XR and MIR results? Because do you have like comparison with them and try to see how they compare?
Yes, they do correspond well, but we're actually still in the process of calibrating the mid-infrared. So when we do that, we'll be using the wet chemistry elemental data and see how well that relates to the mid-infrared. But yeah, you can get elemental predictions from mid-infrared data. Yeah.